School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 4 Forecasting Methods. Unit 16 Time Series Analysis.
After completing this unit, you should be able to appreciate the role of time series analysis in short-term forecasting, decompose the time series into its various components, understand autocorrelations to help identify the underlying patterns of a time series, become aware of stochastic models developed by Box and Jenkins for time series analysis, and make forecast for historical data using a suitable choice from available methods. Introduction. Time series analysis is one of the most powerful methods in use, especially for short-term forecasting purposes. From the historical data, one attempts to obtain the underlying pattern so that a suitable model of the process can be developed, which is then used for purposes of forecasting or studying the internal structure of the process as a whole. We have already learned in earlier unit that a variety of methods such as subjective methods, moving averages and exponential smoothing, regression methods, causal models, and time series analysis are available for forecasting. Time series analysis looks for the dependence between values in a time series, that is, a set of values recorded at equal time intervals with a view to accurately identify the underlying pattern of the data. In the case of quantitative methods of forecasting, each technique makes explicit assumptions about the underlying pattern. For instance, in using regression models, we had first to make a guess on whether a linear or parabolic model should be chosen, and only then could we proceed with the estimation of parameters and model development. We could rely on mere visual inspection of the data or its graphical plot to make the best choice of the underlying model. However, such guesswork, though not uncommon, is unlikely to yield very accurate or reliable results. In time series analysis, a systematic attempt is made to identify and isolate different kinds of patterns in the data. The four kinds of patterns that are most frequently encountered are horizontal, non-stationary, that is trend or growth, seasonal, and cyclical. Generally, a random or noise component is also superimposed. We shall first examine the method of decomposition wherein a model of the time series in terms of these patterns can be developed. This can then be used for forecasting purposes. A more accurate and statistically sound procedure to identify the patterns in a time series is through the use of autocorrelations. Autocorrelation refers to the correlation between the same variable at different time lags, and it was discussed in Unit 18. Autocorrelations can be used to identify the patterns in a time series and suggest appropriate stochastic models for the underlying process. A brief outline of common processes and the Box-Jenkins methodology is then given. Finally, the question of the choice of a forecasting method is taken up. Characteristics of various methods are summarized along with likely situations where these may be applied. Of course, considerations of cost and accuracy desired in the forecast play a very important role in the choice. Decomposition methods. Economic or business-oriented time series are made up of four components, that is, trend, seasonality, cycle, and randomness. Further, it is usually assumed that the relationship between these four components is multiplicative. So the equation becomes xt is equal to TSCR, where xt is the observed value of the time series, T denotes trend, S denotes seasonality, C denotes cycle, and R denotes randomness. Alternatively, one could assume an additive relationship of the form which is xt equals to tt plus st plus ct plus rt. But additive models are not commonly encountered in practice. We shall therefore be working with a model of the form which is xt equals to t s c r and shall systematically try to identify the individual components. You are already familiar with the concept of moving averages. If the time series represents a seasonal pattern of L periods, then by taking a moving average of L periods, we would get the mean value for the year. Such a value will obviously be free of seasonal effects since high months will be offset by low ones. If MT denotes a moving average of the equation that we have mentioned just now, it will be free of seasonality and will contain little randomness owing to the averaging effect. Thus, we can write MT is equal to TT, CT and so on. The trend and cycle components in this equation can be further decomposed by assuming some form of trend. And that is, number 1, one could assume different kinds of trends such as linear trend, which implies a constant rate of change. Number 2, parabolic trend, which implies a varying rate of change. Number 3, exponential or logarithmic trend, which implies a constant percentage rate of change. And number 4, an S-curve, which implies slow initial growth with increasing rate of growth followed by a declining growth rate and eventual saturation. Knowing the pattern of the trend, the appropriate mathematical function could be determined from the data by using the methods of regression as outlined in the earlier unit. This would establish the values of parameters of the chosen trend model. For example, assuming a linear trend gives us third equation which is TT is equal to A plus BT. The cycle component CT can now be isolated from the trend TT in the equation by the use of the third equation. And then we get equation number 4 which is MT over TT is equal to MT over A plus BT. As already indicated, if a linear trend is not adequate, one may wish to specify a non-linear one. Any pattern for the trend can be used to separate it from the cycle. In practice, however, it is often difficult to separate the two and one may prefer to work with the trend cycle figures of equation number 2. That is, MT is equal to TT, CT and so on. The isolation of the trend will add little to the overall ability to forecast. To isolate seasonality, one could simply divide the original series, that is the first equation, by the second equation to get the fifth equation which is xt over mt is equal to tt st ct rt over tt ct is equal to st rt. Finally, randomness can be eliminated by averaging the different values of this fifth equation. The averaging is done on the same months or seasons of different years. For example, the average of all Januaries, all Februaries, all Decembers, etc. The result is a set of seasonal values free of randomness called seasonal indices, which are widely used in practice. In order to forecast, one must reconstruct each of the components of equation number 1. The seasonality is known through averaging the values in equation number 5 and the trend through equation number 3. The cycle of equation number 4 must be estimated by the user and the randomness cannot be predicted. Fitting a trend line. The next step after deseasonalizing the data is to develop the trend line. We shall here use the method of least squares that you have already studied. Choice of the origin in the middle of the data with a suitable scaling simplifies computations considerably. Identifying cyclical variation. The cyclical component is identified by measuring deseasonalized variation around the trend line as the ratio of the actual deseasonalized sales to the value predicted by the trend line. The random or irregular variation is assumed to be relatively insignificant. We have thus described the time series in this problem using the trend, cyclical and seasonal components. Use of autocorrelations in identifying time series. While studying correlation in Unit 14, autocorrelation was defined as the correlation of a variable with itself but with a time lag. The study of autocorrelation provides very valuable clues to the underlying pattern of a time series. It can also be used to estimate the length of the season for seasonality. When the underlying time series represents completely random data, then the graph of autocorrelations for various time lags stays close to zero, with values fluctuating both on the positive and negative side but staying within the control limits. This in fact represents a very convenient method of identifying randomness in the data. If the autocorrelations drop slowly to zero and more than 2 or 3 differ significantly from zero, it indicates the presence of a trend in the data. This trend can be removed by differentiating, that is, taking differences between consecutive values and constructing a new series. A seasonal pattern in the data would result in the autocorrelations oscillating around zero, with some values differing significantly from zero. The length of seasonality can be determined either from the number of periods it takes for the autocorrelations to make a complete cycle or by the time lag giving the largest autocorrelation. For any given data, the plot of autocorrelation for various time lags is diagnosed to identify which of the basic patterns or a combination of these patterns it follows. This is broadly how autocorrelations are used to identify the structure of the underlying model to be chosen. The underlying mathematics and computational burden tend to be heavy and involved. Computer routines for carrying out computations are available. The interested students may refer to Makridakis and Wheelwright for further details. An outline of Box-Jenkins models for time series. Box and Jenkins in 1976 have proposed a sophisticated methodology for stochastic model building and forecasting using time series. A time series may be classified as stationary in equilibrium about a constant mean value or non-stationary when the process has no natural or stable mean. In stochastic model building, the non-stationary process is often converted to a stationary one by differencing. The two major classes of models used popularly in time series analysis are autoregressive and moving average models. For non-stationary processes, the most general model used is an autoregressive integrated moving average, that is ARIMA process of order, and that means PDQ, where D represents the degree of differencing to achieve stationarity in the process. The main contribution of Box and Jenkins is the development of procedures for identifying the ARMA model that best fits a set of data and for testing the adequacy of that model. The various stages identified by Box and Jenkins in their interactive approach to model building are: postulate general class of models, identify model to be tentatively entertained, estimate parameters in tentative model, diagnostic checking, that is, whether the model is adequate or not, after getting an answer in yes or no. Accordingly, use model for forecasting or control. Now let's summarize the unit. Some procedures for time series analysis have been described in this unit with a view to making more accurate and reliable forecasts of the future. Quite often, the question that puzzles a person is how to select an appropriate forecasting method. Many times, the problem context or time horizon involved would decide the method or limit the choice of methods. For instance, in new areas of technology forecasting where historical information is scanty, one would resort to some subjective method like opinion poll or a Delphi study. In situations where one is trying to control or manipulate a factor, a causal model might be appropriate in identifying the key variables and their effect on the dependent variable. In this particular unit, however, time series models or those models where historical data on demand or the variable of interest is available are discussed. Thus, we are dealing with projecting into the future from the past. Such models are short-term forecasting models. The decomposition method has also been discussed. Here, the time series is broken up into seasonal, trend, cycle, and random components from the given data and reconstructed for forecasting purposes. Finally, the framework of stochastic models used by Box and Jenkins from time series analysis has been outlined. The AR, MA, ARMA, and ARIMA processes in Box-Jenkins models are briefly described so that the interested students can pursue a detailed study on their own.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Voiceover by Harpreet Kaur. Edited by Savita. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.